Good day, everyone, and welcome to our webinar. My name is Maryam Singery. I am an Associate Professor of Practice of Architecture at the University of Texas at San Antonio. I'm thrilled to be host for this event. I'd like to start by thanking our speakers for taking the time to share their expertise and insight with us today. We are fortunate to have such knowledgeable and passionate individuals with us, and we are eager to learn from them. I'd also like to extend a warm welcome to all of our attendees. Whether you are joining us from your home office or elsewhere, all around the world, we are grateful for your presence and eager to engage with you. As you see here, the webinar's name is Seeking Strategies in Searing Setting Passively Cooled Mid-Rise Housing. I go to show you the time schedule. It's a 50 minutes welcoming and introduction, and 40 minutes our speaker's speech time, and 15 minutes question and answer. Our guest speakers asking us to everyone to turn on their camera if it's possible. Please turn on your cameras, and welcome to ask your question by yourself, or if you prefer to type it on chat room, is it okay? About our speakers, I would like ask Professor Mark Dekay and Abram to introduce themselves. Without further ado, let's get started. Thank you so much again. So this room is for you, Abram and Mark.
Abram, you want to introduce yourself?
Yeah, sure, I'll do that. So hi everyone, and welcome to this webinar. I hope that we'll have an interesting discussion. Basically, I'm an architect by education and by profession. I come from a practice background. I'm engaged in the academic field as a full-time faculty member at the American University of Beirut, and I focus my work, in fact, and my teaching and research focus on response to climate. So how do buildings relate to the local contextual conditions of solar radiation, wind flow, and daylight? So in addition to that, I actually am interested in materials and the impact that the materials may have on the environment. I have actually designed a project, which is a school south of Beirut that has many different components. It's a mini campus, and except for the auditorium, it does not have any air conditioning. So it just works with cross ventilation, the proper sizing of windows, proper location of windows, etc. So this is a bit the background and what I'm bringing to this table. I, in fact, was awarded the Fulbright grant, and that's where I spent last term working with Mark at the School of Architecture in the University of Tennessee at Knoxville. It was a very, very interesting and productive and efficient time, about 5 or 6 months that I spent there, working in a very calm and rich, productive context, and doing some hiking in the Smoky Mountains in the weekends.
Thanks, Abram. So yeah, he was great. It was really great to have him here. Also because he's quite familiar with Sun, Wind, and Light, which is one of my books, and really, I thought I understood everything, but Abram has, like, if you can imagine, the person who has just the deep knowledge and also can ask all the questions that find every hole in the work and the problem. So it was great working together. I've been here at the University of Tennessee since 2001. So I'm an architect, full professor here. And you may be familiar with some of my work. Best known is probably Sun, Wind, and Light, Architectural Design Strategies. But if you're interested in the more theoretical side, there's also another one called Integral Sustainable Design that uses integral theory to look at 16 different perspectives, different levels and worldview and so forth on sustainable design. And then most recently, I've been working in a kind of split mind mode. One side has been working with Abram and thinking deeply into the topics that we're going to look at, which can get quite technical. And then on the other side, collaborating with the building scientist, Gail Brager at Berkeley. And we just have a new book that's going to be coming out hopefully in the summer. It's called Experiential Design Schemas. So it's about experiencing nature through buildings and the natural forces. So that's us. And let me go ahead and share my screen and see if I can get started here. See if I can play from the start. There we go.
So Mark, sorry. So
Oops.
we will, yes, Anna, she's going to share the links, your academia, academia
Okay.
publication on the chat room, so you can have access to the links of Mark's books.
Oh, thank you. Let's see if I got this right. There we go. Play from the start. Is that working for you guys?
Yes.
You see
Yes.
the main slide? Okay, great.
Yes.
So welcome again, everybody. I'm really glad to be here and to be here with Abram. And thanks, Maryam, for the invitation. We'll do this in two parts. I'll begin and then hand it to Abram for the second part. As he mentioned, Abram came to the University of Tennessee as a Fulbright scholar last fall. And here we are. This is our little off-campus research lab building. It's a kind of an old house from the 1920s. And he came with what seemed like in the beginning a very simple question, actually a couple of questions. The first one is, and I'm paraphrasing here, what kinds of wind-driven passive cooling strategies could we recommend in climates of the Arabic-speaking world? And then secondly, how could this very common typology of the mid-rise housing, which does not incorporate very good approaches to passive cooling, how could that be transformed or adapted? So I'll talk about the first question. Abram will address the second. As soon as we started thinking about the first question, it immediately generated a couple of sub-questions. And Maryam asked us to highlight the research methodology here. So we're going to not so much give a lecture as help to unpack how we've been thinking about this project and what we did along the way and where we hit dead ends and so forth. It's a lot of fun. So the sub-questions were, what are the climates of the Arabic-speaking world? What are they really? And then secondly, what strategies work best in each one of those places? Now, there's a long tradition of looking at climate zones, at least back to 1963 with Victor Olcay's Design with Climate. The idea is, you find a kind of zone of things places that have similar characteristics, and then you could be able to recommend what works and what doesn't work so well with the climate in that place. This is the latest 2021 IECC system of climate zones in the US. IECC, International Energy Conservation Code. It's an evolving system. From where they began, they've now added a zone 8 on the cold side and a zone 0 in the current version. And I think this logic of the evolution of climatic zone thinking for buildings is kind of important, and we're gonna go there because ASHRAE really started off doing this in Department of Energy with a very North American or even continental US centric idea. And they really didn't cover the hot and the cold places very well. Another thing that's been happening is because of climate change, many of the US counties have been reclassified to warmer zones. And almost all the zones that changed between when we started this system on the left is 2003, and on the right is 2021. Almost all of the places that changed got hotter. So you notice down at the tip of Texas, there's now zone 1 that used to only be Hawaii and South Florida. In South Florida, that zone has crept further north and gotten bigger. And also, if you look at the line between zone 3 and zone 4 in the state of Tennessee, you'll see that over on the west side near Memphis in 2003 was the only zone 3 part. Now that line has moved up so that almost half of the state is zone 3, not zone 4. So, and that's happened all the way up. They just keep pushing up further, and that's in less than 20 years. So if you want some, what's happening, there it is. Climate change is real. And notice while we're here that these IECC types, it types the climates as A, B, and C. That is A, moist on the east side, B, dry on the west, and then C, marine out on the west coast. So remember those, particularly the A and the B, because we're going to look at why that doesn't work so well. Here's a graphic from ASHRAE that's useful to decode these zone definitions. This new zone 8 goes from 7,000 heating degree days up to the coldest place on the planet. And then the new zone 0 goes from 6,000 cooling degree days, and then again to the hottest place on the planet, whatever that would be. So they just kind of made some new zones, but they became very large. And now onto our territory of consideration. So we mapped these zones onto, or ASHRAE mapped them, and we kind of cleaned them up. Onto our Arabic-speaking countries, that's everything north of that sort of heavier black line, mostly North Africa and most of the Middle East. The cities that you see there are the most populous cities in each country. So we wanted to pick for the biggest impact where most people live. All of these major cities are found in zones 0 to 3, nothing beyond 3. And not surprisingly, most of them are type B dry cities, right? Not type A moist, although there are some of those. So, okay, we thought this looks good. Now all we have to do is to find some cities, take these cities from each of the zones, and then we can see what strategies work there, what's better and worse. Immediately, however, it seemed that something was off. And Abram, I have to give him credit, he knows the region. And he noted that Jeddah, for instance, and Riyadh were both classified as zone B, 0B, which is very hot and very dry. So Jeddah, however, is by the sea. It's very humid, whereas Riyadh is inland and very arid. So how could these two extremes of humidity, like Miami and Phoenix, imagine they were in the same zone, right? It's like that. So this clearly just wasn't looking good for our idea of recommending strategies by climate zone. So we had a problem. And we put out on the email list, we called up people we knew, we said, what should we do? And so some experts said we should use Koppen Geiger. So we went around and looked at the Koppen Geiger system. You can find it on Google Earth. You can also find it on RTKL's site called Climate Scout. This is from Climate Scout. And they let you choose a zone and then make some design recommendations. And as you can see here, there's not a lot of zone types in our region. There's a lot of red here. And that's partly because like the IECC zones, the Koppen is based on a combination of temperature and rainfall, not humidity. Okay, so when we zoom in, we can see Saudi Arabia here. It looks like this. So it's all one zone. It's all hot, right? It's all desert. It's all zone BWH in the Koppen, hot desert. So again, Koppen has Jeddah and Riyadh in the same zone. And you might say, well, so what? Except that if you are using a system of climate zones to then recommend design strategies, you can't have those two guys in those two cities in the same place. So Climate Scout is recommending the same design strategies for very humid Jeddah and very arid Riyadh. So here you see evaporative cooling, green roofs, water features like a fountain. So that's great if you have dryness, but not great if you have humidity. It doesn't work at all. In fact, makes things worse. So clearly it was not making, Koppen and therefore Climate Scout was not making these important distinctions about humidity, which are driving things like evaporative cooling or dehumidification, latent loads in cooling systems and so forth. So again, zeroing in, looking at our this is the real method here. So we took a look at relative humidity. We looked at it in several ways, annually and for the hottest 6 months. And we've got 20 some odd cities that we're looking at. This is just a sample. And it turned out it didn't work really at all. It failed. So for instance, zone 0 ranges from 14 to 58%. You get 58% in a zone 0, hotter than Miami, hotter than South Texas. That's a lot of moisture in the air when the air is that hot. Zone 2B, supposedly dry, had more humidity than 2A, moist Beirut. And 3A Casablanca, 3A Algiers have the same. So a dry and a moist had the same relative humidity. So this wasn't going to work. We didn't really think it would work, but people said try it out. So we did. Then we said, all right, we remembered there's this white line. And ASHRAE used to publish these maps with this white line that was the warm, humid line. And actually, it was on the original climate zone map from 2003. So we asked again, we're like, guys, do you know where this comes from? We asked all our buddies in the building science world, and maybe they're not old enough to be in our category, and many of them. So that nobody knew where this came from. So we went back into the literature, and finally back to 1993, we found it in the ASHRAE Handbook of Fundamentals, which defines the warm humid zone as using wet bulb temperature. So it's like dry bulb, except, well, you know what wet bulb is. So it's a much better marker for humidity. And so they said if it's 19.5 C for 3,000 hours or more during the hottest 6 months, we'll call that warm and humid. Or if it's 23 C for 1,500 hours, we'll call that warm humid. So we said, all right, let's try that for all of our climate zones. So we got into the hourly data, we ran the numbers on it. We counted up these wet bulb hours in each location above these two thresholds in the hottest 6 months, so we could compare it to that ASHRAE line. And we got some strange and unexpected results. So in the red box here, right, are all but two of the 0B hot and dry desert cities were actually then classified as humid. And also by this definition, probably what shouldn't have turned out this way in our mind, at least, none of the A, that is the moist climate cities, qualified as warm humid. So Beirut, for instance, almost warm humid, but not really meeting the metric. So this metric began to explain, however, the difference between the arid and the humid in the hot zones, even where there was not much rainfall. But we also started to think, well, all right, what about Muscat, Oman, right? This place that's super humid. Is an hour there equal to one in Casablanca? What if the wet bulb was actually way above this 19.5 threshold? So hold that question, because we came back to it. Meanwhile, right, and there's a lot of streams going on, we're posting on really big walls, pin-up walls, 2 complete walls in one room. We're posting, examples of traditional and modern architecture from each of these cities or near them. And we're looking for what strategies are in those buildings, and could that tell us something? And then we're trying to sort these cities into climate types by looking at various metrics. And it's working, and little by little, it's working better and better. And on the other hand, some people said, well, just forget about climate zones. You don't need climate zones anymore. We have computers. Just count up the hours in the different strategies that fall into these different zones on the psychrometric chart. So if you're familiar with Climate Consultant, it uses these overlay strategies based on primarily the work by Murray Milne and by Gavoni, originating with Gavoni's work. And in this case, we first looked at natural ventilation, and it was useless because many of the places are just too hot to open the window most of the time, particularly if you're looking at the hot months. And we started off thinking like North Americans, maybe, let's take the hot months, the hot 3 months, and then the hot 6 months. But the comfort zone in this case is fixed. It's ASHRAE defined or California defined, and then all of the overlays are relative to that. So we settled on looking at direct evaporative cooling, night ventilation with thermal mass or night cooled mass, and adaptive comfort. And so the AC on the little tags here are not air conditioning, it's adaptive comfort. That is how many hours fall into this kind of bigger zone that happens when you take account for the fact that human beings adapt to the place. And this adaptive comfort percentage seemed to be a pretty good metric. So you can see between Riyadh, Tripoli, and Casablanca, the AC numbers get bigger. And that makes sense because the climate is getting cooler. And then with direct evaporative cooling, we saw there was, only 1% in Jeddah and 94% effective in Riyadh. So that's what we were hoping for. That's the kind of distinction that we hope to get in a climate zone. But then another thing came up. It said basically that night cool mass, which historically people would say, yeah, in a desert, no problem, use high mass with night cooling. Well, when it's that hot, it didn't work. And so that was kind of unexpected because it went way against all the traditional vernacular and building science wisdom in the general publications. So meanwhile, right, we decided, all right, let's improve on this wet bulb method and use wet bulb degree days, which we'd never seen anybody calculate, but it seemed like a good idea. So wet bulb degree days are sort of just like heating and cooling degree days based on dry bulb temperature, except we're using wet bulb as a base. So what that does is it says, all right, let's look at the wet bulb temperature, the average for that particular day. And if it's higher than whatever your base temperature is, then subtract the difference. And that's how many degree days, wet bulb degree days you get for that day. Do that calculation day after day after day, and then add them up and you get a picture of the climate, right? So that's how we get heating climates and cooling climates. In this case, we're looking at humidity. And this provided a much better range that aligned better with this evaporative cooling potential that we were looking at. It allowed us to distinguish between cities that were closer to the sea and ones that were more inland in the same climate zone. And then you can see that we tested 4 different base temperatures because we had no idea which one would work the best. And it turned out if you wanted to get some numbers in every climate, we had to go with the 19.5, which fit right aligned with the ASHRAE white line that we were looking at before. So this is a pretty good idea, we thought. And here's all of our study cities that are plotted. And what you see is on the vertical, you have the IECC cooling degree days, base 10C. That's around 50 degrees Fahrenheit as the base temperature. And then the wet bulb degree days I've just been talking about, those are going horizontally. And then the black dots are our type B climates and the white dots are the type A climates. So you can clearly see here that there's no correlation at all between these type A and type B from IECC with humidity, or at least with wet bulb degree days that we're looking at, which is a pretty good indicator. And the reason why they don't is because they're based on precipitation. So we've overlaid there these 3 zones of precipitation. For instance, the big one at the top is less than 250 millimeters annually, right? And so clearly in this region of the world, you can have a city that's dry and considered a desert, but it can actually be extremely humid like these cities in the Gulf. So then we did the same thing with the Köppen. We overlaid the Köppen designations, and that's these 3 bubbles now. And you can also see that it doesn't work at all. It fails for making any of those important distinctions. So it has Casablanca and Beirut in the same zone. It has Kuwait City and Dubai in the same zone. And those are just radically different places. So we're proposing to keep this idea of the numeric zone system, although the zone 0 that's recently been added seems kind of large and almost like we need a zone -1. And then on the other hand, the A, B, and C types that are in the typical conventional system don't seem to work very well. We think there should be some kind of a more nuanced way of understanding places based on their humidity, not based on their rainfall. And then these divisions make more sense in a kind of nonlinear way. So you'll see that the A, B, C, and D are not, even increments of distinction. And that allows us, there's no right answer for that. We made it up. But that allows us to get some distinction between truly arid places like Riyadh and Baghdad, with semi-arid cities like Cairo, with, known humid places like Beirut, and then a whole other category of hot and very humid in the Gulf. And then there's this weird outlier of Muscat, Oman out there that's just, twice as humid as any other place that we studied. So then we just, here's the simplified version. And truly tropical cities like Singapore, they might change this. We haven't studied those places. Most of the region we're looking at isn't in the tropics. Some of it is, but not much. So these wet bulb degree days seem to be a good indicator of dehumidification needs and evaporative cooling potential. And we've also based it on ASHRAE on the hottest 6 months. Now, that may be a problem because some of these places actually need cooling all year round. So again, if we get out of our headspace of thinking about North America, there are places in this region where you can open the window in January and it's just fine. The other thing is that it may be that we should look at something like where this base temperature occurs for heating and cooling degree days. They're using base 10, 50 degrees. That seems to me to be a big building, an air-conditioned building, a conventional climate zone, one with a lot of internal gains. That may make sense in some places. It may not make sense here because almost no one is going to start cooling when it's 50 degrees Fahrenheit or 10 degrees C outside in a residence. All right, now there's one other thing here that sort of changes the whole game, and that's this idea of the adaptive comfort model. Instead of a single continuous zone, you can see the gray background on here. This is Baghdad, and what we're looking at is the temperatures over the course of the year. And that gray would be the comfort zone, and it's changing, it's moving, it's shifting upwards as people adapt to the changing ambient conditions psychologically and physiologically and culturally also. So why that's important for us is that in the typical way of looking at strategies on a bioclimatic chart or on a psychrometric chart, either one, you get a fixed comfort zone. But we ran across Andrew Marsh has an online psychrometric chart, which you can, if you choose the right choices, allow you to look at how that zone moves over time as the climate gets warmer during the year. So we also recognize that the statistical percentages we were getting out of Climate Consultant didn't tell us what was happening every month to month, and whether that strategy was going to work. So what we did is we assessed a series of different passive cooling strategies for each city in each month. We plotted the average day for that month and the design day for that month, which is like the 2% hottest day. So we got the hottest day and the average day. And then we went back to Gavoni for some really simple but useful formulas that don't just say the hot hour or some hour falls into a zone, but says if this is your day and it goes from, cooler at night to warmer in the day, and you have a strategy like high mass with or without night ventilation, what's the temperature going to be inside, right? And so we use this in combination. So now watch what happens. So we're in January here in Baghdad, and if we go to February and then March, you see the zone is moving, April and May and June and July, and the strategy overlays are moving with it, which does something really interesting compared to the previous 20th century logic, which is that because those zones are moving, now the passive strategies, if you take into account human adaptation, they're actually much more functional at hotter temperatures than we thought in the past. So this is the only tool I found that's actually calculating this right now. So over on the right, you don't have to look at all this, but over on the right there, we're kind of keeping track of the strategy works or it doesn't work, what's the inside temperature, et cetera. And then as the climate gets cooler again, you go back towards the winter. Now the zone is moving back to the left. And actually what's happening there is now the passive solar stuff is even working better. The heating strategies are working better because you're dropping that climate zone back down. And then, so we summed all this up, and for each city, we compiled all the results on what we call the strategy glyph. It's a kind of passive cooling signature for the city. It maps 12 months in a circle, and in the center is a kind of comfort rose showing the adaptive comfort percentage for each month, how much you don't have to do anything because it's already comfortable. And then each of the arcs represents the effectiveness of a different passive cooling strategy. And the color range is showing whether it works on the hot day, the average day, both days, it isn't needed, it's too cold, you don't need cooling at all, so forth. So in Baghdad, what you can see is it's too hot for 5 months for anything other than evaporative cooling. None of the passive cooling strategies of high mass and ventilation and so forth, they're only working for 2, maybe 3 months out of the year. So kind of interesting to me anyway. I won't spend too much time on this, but these two guys are in the same climate zone. This is Sana'a in Yemen and Amman in Jordan, and they have almost identical cooling degree days. So put them in the same climate zone exactly, and similar humidity. They're both quite arid. The difference between them is elevation. So Sana'a is higher elevation. It has a milder winter that's longer for more months. So in terms of cooling degree days measured, with the metric, it's similar to Amman, but it's not nearly as extreme. And that's why, that's why the passive cooling stuff, it looks completely different. So just about to wrap up, I want to take you on a couple of little quick tours here, right? So just to get the sense of where we're going with this. So I'm going to show you hot zones. They're all zone 0 and 1. So, Miami and hotter, right? And in this case, though, they're all arid. So they're all arid places with very low humidities. So starting off with Kuwait City, zone 1, and what you might want to watch is also the wet bulb degree days. So very low wet bulb degree days, and evaporative cooling, right? Really important, really effective. Zone 0, Khartoum, Sudan, really hot, right? But it gets too hot for evaporative cooling at some point. 484, right? Now it's 2 months of too hot. Right now, a whole series of months that are too hot in Abu Dhabi for passive cooling, but over there we start to see passive cooling in the wintertime, right? Doha, even more, even wetter or more humid. Dubai, continuing to get more humid, and ending up with Muscat, the most extreme in our whole series. And look, half of the year where the passive cooling is being the most effective, and ventilation and night cool mass, it's in the winter side. So here we are on the left, super dry, on the left, Kuwait City, zone 0, same zone in terms of cooling needs or cooling degree of cooling needs in Muscat, but way more humid, right? And IECC has these in the same zone. So we think maybe something's coming. We've hit on something here. Now, one more little quick tour. This one is going from hot to cold. So before we just went from arid to humid. Now we're going on the dry side, all arid. We're going from zone 0 to zone 3. So again, starting with Kuwait City, zone 0, very extremely hot, searing, you might say. Right? Zone 1, Baghdad, also really hot, right? Also really hot, where evaporative cooling is the only thing that's working for 5 months. Zone 2, now we're cooling off a little bit. We're starting to see zone 2 is like San Antonio's a zone 2, right? But it's an A type. It's a bit more humid. These are much more arid. So this is like Phoenix, right? Zone 3, now we're cooling off even more. Zone 3 is like Atlanta, I think. Yeah, zone 3 is Atlanta. Or now southern part of Tennessee, Memphis. And then finally, zone 3 with the most cooling degree days here in Jerusalem. And then just ending again with that comparison between the really hot zone 0, arid, searing, and zone 3, Jerusalem, still warm, right? Still what we consider to be a hot climate, still arid, but way more opportunities because of the degree of the heat or less heat, way more opportunities for a variety of different passive cooling systems. All right, well, thanks everybody. That was a little more time than I hoped to spend, but I seem to extemporize a little bit. So we're, about the halfway point here. I'll hand it off to Abram and hope to follow up later with some questions and conversation.
So just give me a second to...
Switching to Beirut.
Exactly. So share. Okay, so can you see the screen?
Yes, we can.
Perfect. Okay.
Thank you.
So thanks, Mark. That was, in fact, brilliant by way of condensing the 5 months into this presentation. So at this point, I'll be continuing. So as mentioned earlier, right, this is we divided this presentation into part 1 and part 2, but in fact, this was work that was all done in parallel. And at this point, I'll be looking at the cities and the buildings more closely, and in particular, of course, this mid-rise residential typology. So if we look at and analyze cities in the Arab-speaking world, we can identify numerous commonalities in the urban morphology, right? So I will be going through a series of 5 or 6 cities. I'll scroll through the images, and then I will describe some aspects of these commonalities. So first of all, you will see that the buildings are of unequal heights, right? There's no planning metric or planning system that identifies particular heights. This is based on exploitation rights as related to particular parcels, etc. And the result is, in most cities, this type of morphology whereby buildings, although could be adjacent buildings, have very different heights. A second is, in fact, the relationship to the streets and to the public space. And this is what identifies the orientation of buildings. So buildings are oriented in a way such that the public areas in the apartments, living, dining, etc., are always towards the public component in the city, such as a street or a garden, if there's a garden, and the private areas are to the other side. And this creates particular conditions of planning, of interior planning. Another aspect of these cities is the very different window to wall ratios on the elevations, right? So you may see elevations that have a lot of glazing and some elevations that have much less. And this is related to the internal aspect of the internal planning of the apartments, mostly related to the privacy issue, right? And this is not really relating in any way to the environmental parameters, whether wind flow, prevailing winds, or incident solar radiation. Another aspect is that what is common in all of these cities is the use of cement-based materials. So most of the buildings are built with cementitious materials. This is very common in this part of the world. Of course, I'm relating to the structure, a reinforced concrete structure, as well as the opaque component of the facade. The rest, obviously, would be, the rest of the facade would be made out of glass, again, different types of glazing. And another commonality is the prismatic shape of these buildings. So most buildings, the shape is derived from the particularities of planning of the apartment layouts, let's say, depending on how many apartments there are per floor and how many floors are actually allowable to be constructed in on a particular plot. So the urban morphology can be described as having disparities, right, between high-rise, mid-rise, and low-rise buildings, which are in many cases close to each other. The cities are having there are adjacencies, let me say, between old buildings and new buildings, and usually this also contributes to the height. Older buildings are lower, newer buildings are higher, again due to the developments of the building law and the exploitation factors. And lastly, the aspect of the negative component in the city, right? These are streets that used to be narrower, and then with the advent of technology and cars and etc., today we have in most of these cities wide highways that divide the cities in various directions, right? Basically related to the transportation diagram of a city. And so And so this could kind of summarize, if you like, the morphology of these cities that we are looking at. So again, as Mark mentioned, it's important to note that these are the conditions of cities today. However, we were also looking at how did these cities, what types of buildings existed in these cities in terms of vernacular typology. So way before the intervention or introduction of mechanical systems, as well as buildings during the modern era, right? This is a very interesting stage in this part of the world. Modern era, basically 1940 to 1970, let's say, whereby there were buildings. So at that point, the introduction of cement was done into the cities, so the technology was advancing, yet air conditioning systems were not very common and they were not widespread into these cities. And so therefore, these buildings, although they had multiple levels and started to become taller, did in fact relate to the climate by way of addressing prevailing wind directions and incident solar radiation, because they could not rely on air conditioning systems to maintain indoor comfort. This is a selection of buildings that illustrate the commonalities of buildings found in these contexts. So today we find, as mentioned earlier, very different climate zones in the Arab-speaking world. However, the typologies of the buildings are very similar, right? You will see similar use of materials, similar heights, similar window-to-wall ratios, etc. And the characteristics of these contemporary buildings, I summarized them in these 6 bullets, in these 5 bullets, right? So if we take a deeper look, which will allow the identification of the following characteristics for a mid-rise residential building typology, this will, as you will see in a bit, inform the opportunities that may result from this methodology and this approach. So there's always a vertical circulation component and a service core in these buildings, right? We're talking about mid-rise. It's important to mention that these are buildings that are from, let's say, 8 to 15 floors. And so therefore, there's always a vertical circulation, stairs, lifts, at least one, as well as other vertical components that are all included in this core. So it is found in pretty much all buildings. If this component is designed to serve for natural ventilation, it can accommodate for different strategies. Okay, and this is where this becomes really interesting, as we will see in a bit. So depending on the site's wind condition, vertical wind flow can so upwards or downwards, basically in the form of stack ventilation or as a wind catcher, can help the natural ventilation mode in this in such buildings. The fact that there are always 6 to 15 floors is kind of the general level number of floors that is existing in these buildings. So this is important because it allows for different ventilation strategies, or it requires, let me say, to be more correct, different ventilation strategies at different floor levels, right? So this is affected, of course, by the exposure, the orientation, and we have to say the air quality. So this makes it possible to integrate a variety of wind strategies, because at the lower levels, usually buildings are more obstructed to wind flow, which differs when you get to the mid-level of a building, and then buildings become much more exposed to the prevailing wind direction at the higher level. There is another interesting particularity, which is that the higher the building, the more basements there are, right? And that also provides an interesting opportunity because of the contact with the ground. So everything that is below ground has more surface area in terms of contact with the adjacent soil. The fact that most of these buildings, the vast majority of buildings, are built with reinforced concrete is also very relevant. These are, of course, columns, beams, shear walls, slabs, as illustrated in this picture. This heavyweight construction, which of course has a heavy thermal mass, usually decreases from the center of the building towards the periphery. So we can see patterns in terms of structure whereby the central core is the most massive component, and then as you go outwards in the building, it becomes less. There are also other particularities, which is the fact that at the lower level, the sections of these components are thicker and bigger, let's say, bigger cross sections, because they're supporting more weight. And then as you go up, you may find smaller structural components. Although this is a hot part of the world, in many parts and in many, let me say, contexts and at different times of year and different times of day, so this could be in the evenings, etc., outdoor spaces, balconies, terraces, loggias are of utmost importance, right? These contribute, so other than the environmental aspect, other than them being a climatic buffer zone between the exterior and the interior zone, or the interior space, they also contribute to the social mixity and social richness of this area. And so they vary a lot. These are very common, but they vary in terms of configuration. So these may be recessed within the building, these may be protruding, these may be in the form of cantilevers, so on and so forth. And again, we will see how this could be an interesting opportunity. They also, by the way, we're talking mostly about wind, but these can also help in terms of becoming shading devices to particular elements on the facade. As you can see in these diagrams, so these are schematic mappings of floor plans of these buildings, right? So these buildings most often than not have multiple units, multiple apartments per floor. So a schematic representation shows 2 apartments per floor with the core in the center or the core at the periphery. Both are very common. You will see in the middle diagram 3 apartments per floor with the core indicated in this orange rectangle. Of course, the gray are the balconies or the interface, let me say, this buffer zone between in and out. And on the right, there are 4 apartments per floor. So these spaces within the spaces within each apartment, so each one of these blue elements, blue rectangles, is an apartment, and inside of it, each of the spaces, so bedrooms, living, dining, service, kitchen, etc., would have different orientations, right? Different exposures to prevailing winds, depending on how the floor plan is designed. In addition to the actual building itself, it's so important to look at what is happening around the building. So the negative space surrounding buildings can be instrumental in allowing or obstructing wind flow from a particular site, from a particular building. This negative space is a function of, in fact, depends on the width of the streets. So here there are some illustrations showing that. The width of the streets and sidewalks, the piazzas, and of course the heights of buildings. So these are aspects that need to be studied as particular conditions for each site. In addition to the negative space, it's important to note that as shown in this diagram on the right, the urban morphology, the level of air pollution, the building and street materials are all affected by the prevailing wind direction and the incident solar radiation. And when they are affected, they will in turn affect the actual building in terms of contextual condition. This is a schematic representation of an approach of this methodology that is being adopted here. And it's addressing the aspects in the following steps. So number 1, there are 5 main or basic approaches or steps, let me say, sorry. The first is starting with the project's context. So it's building use, right? What is this building used for? And the spatial requirements, the program. Also, it relates to the applicable strategies to the prevailing wind direction. So we can look at the glyph, the city glyph at this point, and identify what are the applicable or the useful or the efficient strategies that are applicable to this site. Second, we would analyze and assess the availability of wind on site, both in plan and in section, right? So is the wind reaching the site? And if it is, what is happening at different levels? Again, this is very important because of the difference in heights and of what's happening in the context. In number 3 here, step number 3, we are again looking at the city glyph. So we're looking at this glyph for, it's providing 2 levels of information. First is what are the important or efficient strategies and what's happening during the year. And the second here is to what extent within each month is the strategy useful within this particular context. And this, of course, leads to the identification, as you can see here, of these strategies. So cross-ventilation, having a wind catcher, the stack, evaporative cooling, nighttime cooling, and even ground cooling. Step number 4 would lead us to so this is basically the interest in terms of architectural design for the architect and the design team to think about ways that these strategies can be integrated into the project. And 5th step is, in fact, the assessment that is doable at the early stages of the design process. We can consider having this type of matrix, so a matrix that documents the strategies that are considered by the architect and the design team, right? And this matrix would be particular and customized to a particular project, depending on the use and depending on the orientation, pretty much resulting from the analysis of the city glyph we saw before. So in addition to identifying the strategies related to the building components and assigning primary and secondary, as you can see here, there are 2 levels of blue. So there are strategies that may be of primary importance and other strategies that may be of secondary importance. And this relative approach can also be instrumental in guiding the design approach and the design team working on a project. This is, in fact, a picture of one of the walls, as Mark mentioned earlier. So this is another wall in another space. And this is a flow chart that is basically going through the whole process of identifying, or let me say, relating the mid-rise typology to wind flow. So it would start by defining the climate zone, as we saw earlier. Then the design team would look at the city's wind patterns, right? What are the available wind patterns on that site, and the prevailing winds, how they differ during day and night, how they differ during seasons, etc. After addressing wind at the large scale, you want to conduct a more confined study of wind availability on the site itself, the site where the design team is studying a project. And so considerations of the roughness of that city, right? The density of the city, the roughness in terms of building configuration and building morphology are very important. Topography is also included, as well as the microclimate conditions of the site. So all of these parameters are addressed together to identify what is happening at the site. A good way to understand climate is, in fact, to have a weather station on the site. And in some cases, if that's not possible, then information has to be extrapolated from somewhere else, or in fact, it could be simulated. So once we look at the particularities of the site, we, in parallel, are looking at the actual building typology. So here we want to identify or distinguish 2 different main aspects. So does the site receive the prevailing winds, or does it not receive prevailing winds? This is an important aspect to kind of define at the early stages. So if the prevailing winds access the site, this gives rise or potential to a set of strategies. If it doesn't, we need to use other strategies. In parallel with that, we're looking, as you can see in this diagram on the top left, we're looking at the building morphology, right? So does it have 1 core? Does it have multiple cores? How many floors, etc.? This all becomes very relevant because I'm thinking about the wind as well as the building itself. And you can see in the colored, let's say in the colored diagrams here, in the middle of the slide, these propose some transformations to the massing layouts. So there's a particular massing, as we saw in a few slides before, and these massing layouts can actually morph or transform, let me say, so that they enhance the wind flow inside the actual building, inside the spaces of the building. And this is, of course, relating to the prevailing wind directions that are available. If there are no prevailing wind directions, we have to rely more on buoyancy-driven ventilation. And this is where we kind of need to trigger wind flow inside the building by creating areas of different pressure and different temperature. And then once that is, after a thorough, let me say, a thorough assessment of wind availability and building configuration, the architect and the design team here can study numerous strategies, as shown in these post-it notes here. So these are just sketches documenting what are some options that could be applied. So these numerous strategies are compatible with the contextual givens, and they include cross ventilation, the wind catcher, the stack ventilation, evaporative cooling, and mass cooling. Right? So there are ample possibilities. The idea of this slide is to show that this is by no means confining the thinking mode and the approach. On the contrary, this is to actually open up the potential for exploration and for design options. I'm showing here this. So in terms of assessing the strategies at the early design phase, this is in fact an example of that assessment. So this is a particular strategy, which is stack ventilation. We would start by getting the wind pattern from the airport, as you can see at the top row there. So because in most cases, the airport wind information is available. Then using a software from the Danish wind industry, the one that's shown in the upper diagram with the red rectangle. So this is the Danish Wind Industry Association. We can actually get a better understanding of what is happening to the wind at different heights in a particular site, based on the roughness of the context. So again, this comes down to, on one extreme, we have a very urban context, and on another extreme, we have, let's say, rural or even open fields. That's the other extreme of roughness. So looking at that, it's a free interactive software that is online. And so we can get an understanding of what's happening at the different heights. We can, of course, double check. It's always good to double check. So the graph in the middle is from the book, from Mark's book, Sun, Wind, and Light. And it can be used to actually identify the what is happening in terms of wind, and to counter check the chart above. After that, so once we understand what's happening on the site, we can use again the graph below to identify what is the section that is required for stack ventilation, right? So this gives the sectional area of the stack that is required to make stack ventilation efficient. It's very interesting to note, here it's probably difficult to read, but in that small orange rectangle, I actually did multiple runs to see what is happening at different heights. So at 3 meters, 6 meters, 9 meters, these are at every floor. And you will see that the stack actually differs in terms of sectional dimension or sectional area. And that could be really, from an architectural perspective, very interesting input that can inform the design of a building, and in particular, the design of the core. So this is, I hope this was clear. I tried to summarize the whole approach. In conclusion, I'd like to end here by saying that, well, this is where we are in the journey. The takeaway message here is that it lies in identifying the opportunities, right? We're trying to flesh out what are the opportunities to be able to design these mid-rise residential buildings that are very common in the Arab-speaking world, and that, as we were discussing maybe before the presentation, will become hotter contexts as we move into the coming decades. So it's really important to look at these. So we presented insight regarding our approach and methodology, and some preliminary results, as you can see here, are in fact that the apartment plan configuration, either it's on one level or two levels or maybe more, is so important to enhance indoor ventilation. The second component, so first component is indoor space, second component is the outdoor space, or maybe I should say the buffer between inside and outside. Again, how that is configured in a project, this buffer space does not have to be the same on all elevations, because if you relate it to wind flow and capturing wind, it could be very, very useful as a strategy. And so therefore it could vary depending on the orientation with respect to wind. And the third is in fact the core, right? This vertical component which exists in all buildings. And there are so many possibilities and options, either having one core that works all together, or subdividing this core into different zones. So after 5 or 6 levels, the efficiency of the core will reduce significantly. So this is where we can subdivide the building into sections and have cores that work in parallel. This is in fact the summary, if you like, of these of the preliminary results. Again, I'd like to thank, of course, Fulbright for allowing this to happen. I want to thank Mark and the School of Architecture. You know, this was brilliant, and Mark's support and his generous contribution in terms of time and knowledge were priceless. And I want to thank the graduate assistants, so Perto, Munzir, and Zach. They did a great job in researching the vernacular typologies, the modern typologies, doing some test runs on the implementation of this methodology, and illustrating the information on these city glyphs. I've provided here some references in case of interest of what was used in this part of the study. And I will stop here and open it, hopefully, Maryam, for up to you.
Thank you so much, Abram and Mark. It was amazing. I mean, it was very informative, engaging, and thought-provoking speech and research, and methodology was amazing. Thank you. I am sure you did so much work. So now we encourage you to actively participate in the discussion by asking your questions, sharing your own insights, and interact with other attendees. Unfortunately, we would not be able, co-host and myself, we wouldn't be able to turn on the cameras. So unfortunately, we will not be able to have the attendees, the cameras. So, but they can ask their question if you have any question, please go ahead. Let me go to the Anna.
Yes, I will start by reading some of the questions in the Q&A box. If someone would like to add any questions, it can be done there, or you could ask them yourself.
Yes, you can ask for yourself. Yes, please. Go ahead.
I will start by reading Doug Long's question. It's concerning mid-rise buildings. How viable are these strategies in consideration with San Antonio or South Texas? In other words, would it be effective to implement some of the techniques discussed into our local architecture? And if not, are there strategies you would recommend over others for San Antonio's climate?
So yeah, let me, I'll start by answering that, and then I'll give it back to Mark, because I'm not very knowledgeable about the climatic conditions. So I want to maybe clarify that what was done, what we presented, in fact, is a methodology, right? So in fact, different parts of the planet would require a similar methodology, but maybe the components and the parameters are different. So so if the building type in San Antonio is similar to this mid-rise situation, I mean, if it, of course, it would have a core. If it has multiple units per level, if it has this in-out buffer, then this could potentially be applicable. I give a lot of importance to materials, right? The fact that these buildings in this part of the world are built with high mass materials, cementitious materials. Of course, it has some disadvantages at other levels of waste, etc. But from the perspective of relating to these strategies, whether wind or solar, there are some advantages. So again, this would relate. I'm not really familiar with the building techniques and assembly methods that exist in San Antonio. But having said that, I think the methodology is applicable to other areas on the planet. Yes. Mark?
Yeah, I would agree. The mid-rise, however, is probably not nearly as common in most U.S. cities, except when you get up to a certain kind of density. It is, however, as you saw from the photos that Abram was showing, very, very common around the world, particularly in hot climates. So in climates that are frankly hotter than San Antonio. But San Antonio's, I think, a 2A, which is similar to Beirut, although I don't think it's quite as humid as Beirut. So actually, in American cities, what we have is much lower density, much fewer stories in general, right? Not necessarily in center cities, but most of our housing, if you're not looking at the center city, is low rise. And so that all makes everything easier. Right, so all of your passive systems were probably better in that kind of context than they work in a really dense one, where you have to do a lot more assessment as to, where the wind's coming from, and is all of that urban fabric upstream beginning to block your wind and so forth. So yeah, great question. I think certainly you can do a lot of passive cooling. There's some great Texas firms that are showing how to do that.
Yes.
Thank you for your answer.
Anna, let me ask Derek, could you please, could you please ask your question by yourself, Derek?
Sure. Given how fast you've shown these different climate zones to be changing, how should we be thinking about designing buildings today in terms of, should we be anticipating what the climate looks like in the next 20 years for what we're building today? Otherwise, it seems like some of these passive strategies, if you're not designing for what the climate's going to be, could become outdated faster than the buildings that we're building today.
Yeah, that's a great question, Derek. Certainly, we have to be thinking forward about the resilience. We don't know exactly what scenario we're going to be living under in different parts of the country, or how bad it might get in different parts of the world. But we can imagine that most places are going to get a little bit warmer. And a couple of degrees might make a significant difference in a climate zone. It's probably not going to make or break your passive cooling system. And I think you're right to think about whether, how long the building is going to last. So let's say that you're looking at a building as a 100-year decision. It could be longer than that, right? So the average lifespan of average life of a building in the UK is older than 100 years, I believe. And so we need to be looking out, right, into some future timeframes in which the energy sources that we use today are going away, that the renewable sources are continuing to be present, and that we have to think about that in one way or another, I think. So yeah, I think that's What are you gonna say over there, Suzanne? Suzanne's over here trying to send me a message.
Well, I think basically passive reduces CO2.
Oh, okay. So she's making the climate change argument over here that, and I would say that's true. If you're going to be looking at how you're going to get to a net zero building, and you do it without thinking about passive heating and cooling in our climates, because almost every US climate is a mixed climate, has some cooling, some heating. You can't really get there. You can't really get there. You need to get your loads down by 70 or 80% relative to conventional dumb practice in order for the renewable system to be, sized at an economical cost and at a system size that's going to, let's say, work on the space that you have on your building or site. So in my mind, you start with the fundamentals. You start at the bottom of the kind of hierarchy, which is with, first of all, the archetypes, with the building type, with things that, have been around in vernacular architecture for a long time and that people got right in most regions. And you build on top of that the passive systems. And then only the kind of cherry on top becomes the renewable energy system, the green power and the high efficiency machines and the high tech glazing materials and so forth, because those things are going to remain expensive. They're going to remain out of reach for most building owners, most poor people around the world. And we're talking like billions of buildings that we need to, solve. We now have more buildings on the planet than ever in, all of human history combined or existing right now today. And we're going to be, rebuilding, a Manhattan sized amount of building stock every month on the planet, right? Every month, a new Manhattan pretty much is coming out for the next 40 years or so. So we got a lot of work to do and a great opportunity for architects right now. So this is an exciting time to be an architect, I think.
Thank you, Mark. I see Danny. Danny, could you please ask your question if you are here? And then also, could you please introduce yourself?
Hi, my name is Danny, a student in Beirut.
Oh, okay. Thank you so much. Okay, go ahead.
Yeah, my question was about core ventilation, but I mixed it up with stack ventilation because I didn't know what core ventilation was. But for stack ventilation, does the ventilation that goes in, if the building is higher than 6 floors, does it become ineffective as the building goes higher? And how do we fix that if that's the case?
Yeah, Danny, so interesting and important question, right? So it is, in fact, of course, yes, there are limitations. So you are, the assessment is correct. However, this is as I was trying to explain, this relates to many givens, right? So how is the building exposed to wind? First of all, of course, is it exposed to the prevailing winds or not? So these are different, these will lead to different avenues of investigation, let's say. So it's much easier if there is prevailing winds, if there are prevailing winds on the building than not. But having said that, if there are not, you can actually use the core, right? So the core is the central component. It's the backbone of this building that includes the stairs, the lift, etc. And so that element, if designed in a way to accommodate for wind flow, can actually do quite a lot. And 6 levels is not a lot. I will give by example many buildings in Beirut that were designed in between 1955 and early 60s. And these were buildings that were very often 6 or 7 floors high. If you visited these buildings, the stair was not like the stairs that are in today's apartment buildings, which is completely small and tight and put in some dark corner, right? These were stairs that were very interesting in the middle of the building. You always had space between the flights, so you would go around, some negative space going up. And these buildings actually worked quite well in terms of accommodating for natural ventilation within the building. So I always like to bring this back to the social aspect. So in these buildings, people actually used to open their front doors, their apartment doors, and they could they could benefit from the wind flow in the building. And in some cases, when the landing was wide enough, people actually sat there. So it became a place for social interaction. So yeah, it is doable. If you go beyond, it needs further study to make sure that it works or not. That's where I was saying that maybe one consideration is to subdivide the building to have multiple stack ventilations that are based on different approaches. So one could be a place relate to prevailing winds at the upper level, maybe buoyancy at the lower level, so on and so forth.
Yeah, I think Abram has hit on a good strategy there that showed up. He helped me with a studio we were running with design students, and we had some sites in Beirut, one of which was in Hamra, which was fairly dense, and it became kind of clear that down at the street level, there wasn't much wind, and up at the top, there was much more access to breeze. So this idea of beginning to zone the strategies vertically, like he's talking about, so it looks like a real sensible opportunity. You'll also find, when people are doing stack ventilation schemes with open cores or with sky lobbies or sky gardens in high rises, they tend to divide it up right into sections. I think socially, for one reason, you don't want to be looking down 30 floors. Why not look down just a few floors to a garden? But also the air velocity in the stack ventilation can get quite high if the building, if the core is also very high. So people are exposed to that. That's one reason for beginning to subdivide it into sections, and that still works. You don't have to have that core run continuously open all the way up. So, great question.
Thank you so much. We have 3 more questions. So Dante, could you please ask your question and introduce yourself too?
Sure. Can you hear me?
Yes.
Okay.
Yes.
So I'm a student at the University of Texas, San Antonio. I'm one of Maryam students in a graduate program. But my question was due to I think you kind of already answered my question. I kind of typed it after you answered the first one, but it was mainly due to the density difference in San Antonio and other North American cities. Couldn't passive strategies be more feasible since we don't really have large cities with high or mid-rise buildings other than in New York and the upper state cities, as well as how resilient are these strategies that we explore today to different climate zones and stuff. But I think you kind of already touched on those topics.
Yeah, we did hit on them, but I think it's worth mentioning that almost all of the passive strategies started with low rise, low density, or low rise, high density, depending. So the only thing that the high density actually makes more difficult is a wind-driven strategy or a direct solar access strategy, so that you have to really begin to pay attention to how to get the sun to each unit, how to get the sun to each building and on the winter side. And then, if possible, how to get the breeze to each building and to each unit. But if you can't, then there's, then you go to another set of passive strategies, where, for instance, you're making your heat collection in a more concentrated area in one portion of the building and then moving that heat to another place. Or you're using other kinds of strategies like, in high density situations, you'll see wind catchers, particularly in the Middle East. And that's a great strategy almost for any place where one building is blocking the wind upstream for another building, as long as you're looking at a certain kind of low rise to mid rise. The high rise has plenty of access usually itself, and it doesn't really form the problem. So I would say, yes, absolutely. Take a look at the 100+ strategies in sun, wind, and light that are there: heating, cooling, lighting, power, ventilation, and so forth, with a real emphasis on the passive side. We really have a long research and practice tradition over the last half of the 20th, since the middle of the 20th century, I would say, in the US as a good place to take a look at examples of those.
Thank you.
Thank you.
Okay, thank you. We have actually, yes, two more questions on chat room. I go ask Anna, could you please read these
Yes.
two questions and then, yes, because of
Okay.
time. Yes. go ahead.
Rashida Noor asked, during your study of the traditional architecture practices, are there some strategies that you found very useful in today's scenario where the construction practice has evolved so much and the climate has changed?
Yeah, so what's really interesting in looking at the vernacular and these older typologies is to understand the synergy, right? You understand how did the materiality of the built space relate to the particular context and the in specifically the climate, right? So these are important aspects that one could abstract. Of course, as the question says, everything has changed, right? The technology, the technicity, the scale, even the climate. So there are multiple variables that are changing in a dynamic manner as we actually progress through time. So it is not I just want to clarify that the intent of analyzing the vernacular is not to take aspects or components and see how we can apply them, right? This is, for me, I mean, this is not really doable at this point because of how the society and how technology is changing. But understanding the basic synergies, as I mentioned, the harmonious aspect between the building, or let me say the built environment and its broader context is a very relevant issue that, if understood correctly, could translate into how things are being done today or in the future.
Thank you. And then I got to read the last question. Crystal, she asked, which programs did you use to do climate analysis? Which programs did you use to do climate analysis?
Yeah, we were actually we were using Climate Consultant for part of that. But then we used for the psychrometric charts I showed, there's an online chart. If you search for Andrew Marsh psychrometric chart, you'll find that. So we use that. But we also use quite a bit of just our own custom analyses. So if you go, one good site for this is the CBE at Berkeley. There's they call it the CBE Climate Tool. You can do various analyses online there. And you can also download the analyzed hourly data files that for the analysis that they've done. In some cases, we just used TMY data files and ran our own formulas using Excel and so forth. It's kind of labor intensive. So what we're hoping to do now, the next stage is Abram is working with some folks in computing at UAB. And we're hoping to automate that process so that we ideally could then load up any particular scenario, any particular kind of climate file, including something from like a scenario from climate change in the future, and then see what happens. And you know, just related to that question, the previous question, I think now we can also look not only to our own kind of climate zone and region, but we can begin to look at places that are actually hotter than where we are. So, you know, begin to look further south or, you know, further into a slightly warmer place and see what they were doing. And that might begin to give us some strategies about what to do in the future. So, for instance, in Knoxville, there's not a lot of buildings that pay a lot of attention to shading. We're in zone 4. If you go down to zone 3 in the, you know, down in the region, you know, between Atlanta and the Gulf Coast, you start to find quite a bit more attention historically to outdoor living and to shading of outdoor space and shading of windows and so forth. So all of those kinds of logics now can be applied, because probably where I am in Knoxville is zone 4, it'll probably be zone 3 in the future, right? Just like other ones have changed in the past 20 years or so.
This is interesting. Thank you so much. I appreciate that. So I would like to just thank you again, Mark and Abram, for presenting and sharing your amazing research. We learned a lot. It was really nice. So thank you so much. And thank you for all of you attendees for joining us today. And in a chat room, I found some people from other countries. Thank you all to joining us. If you have any other questions, I go write my email address over there, so you can ask questions, or you can find the email address of Mark and Abram if they let us to contact you. So yes, we will keep in touch. So thank you all. Have a good day. I have a good time. Yes, day for us, night for Arams. Okay.
Thank you, Maryam. Thank you, everybody.
Thank you.